Hello everyone, welcome to my talk. Today I will present our recent work on the curves of correlations for robust fingerprinting of relational databases. My talk will be decomposed into the following parts. After giving the background, the motivation, and review the related works, I will give an overview of our work. And then I will dive into the identified correlation attack for database fingerprinting, and then talk about the corresponding mitigation techniques for the attack. And finally, I will conclude the paper. Nowadays, relational databases has been very popular. It is defined as a set of data records with the same attribute. On the right, we have a toy example. Each row is identified by an attribute, and each row is identified by a prime key. The sharing and the releasing of databases is also very critical to a vision of a data-driven future. For example, we can offload our database to Amazon Cloud to benefit from the high computational power. But during the sharing and releasing of database, the owners want to make sure the shared databases are only used by the authorized parties, and at the same time, this encourages them from releasing their received databases to other unauthorized parties. And the database fingerprinting has been developed as a tool to identify the source of the data leakage by embedding a unique mark in each copy of the shared database. Here is an illustration of a database fingerprinting scheme. There is a database owner called Alice. She has a database. When she wants to share the database to different service providers, she first generates random fingerprint string for each of the service providers. And the fingerprint string are randomly generated binary sequence. And the fingerprint insertion process is done by selecting random locations in the database and change the value at these locations using the fingerprint string. Now suppose there is a bad people who have leaked its received database, then Alice will know this one should be responsible for the data leakage because the leaked database contains its unique fingerprint. Most of the existing fingerprint schemes for databases do not consider the correlations among data entries. However, the correlations are ubiquitous in different types of databases. For example, in a demographic database, the zip codes and city names are correlated. Or in a genomic database, the data record of family members are correlated. As a result, the malicious service provider can utilize the knowledge on the data correlation to detect and destroy the embedded fingerprints to escape from being accused by the database owner if they want to leak or pirate the database. In the paper, we show that existing schemes are vulnerable to the correlation attack. And to mitigate against the identified correlation attack, we also propose a robust fingerprinting for the databases. In the literature, fingerprinting usually consider multimedia data, for example, the videos, text, and image. Database fingerprinting is proposed in the first reference. This is a seminal work on database fingerprinting. It allows small error in a market database, and further people have extended it by enabling the insertion and the extraction of arbitrary bit string in databases. Recently, researchers have considered the correlations of individuals' data record in sequential data when generating a fingerprinted version of the sequential data. So our work is different with the previous ones because we consider both column and row-wise correlation in a general relational databases, and where it may contain a large amount of data records. And we also consider different utility requirements when generate a fingerprinted database. Now let me give the overview of the work. First, let me talk about the naming convention of a fingerprinted database. R tilde, we use 3 parameters to represent the techniques used to generate the fingerprinted database. First is alpha. It is just the vanilla fingerprinting scheme, which means it does not consider the correlation. Beta and eta are our proposed mitigation technique against the row-wise and column-wise attack. In the first figure is the scenario that the database owners only share a vanilla fingerprinted database, where the last 2 parameters, beta and eta, equals to the null set, which means the mitigation technique is not applied yet. We know that in most of the cases, this database is already robust against random bit flipping attack, which means if the bad guy randomly changes some entries in the database, then Alice will still accurately accuse it for the data leakage. But if the bad guy launches our identified column-wise correlation attack or row-wise correlation attack, or the combination of them, then with very high probability, it will cause the database owner to accuse other innocent service providers for the data leakage. Finally, we show that if the database owner further apply our proposed mitigation techniques after the vanilla fingerprinting scheme, then even though the bad guy still use the correlation attack, then the database owner can still accurately identify that this one should be responsible for the data leakage. In the paper, we use S prime and J prime to denote the database's priority on the row-wise correlation and column-wise correlation. And we use S and J to represent the malicious service provider's knowledge on the row-wise and column-wise correlation. Now let me dive into the identified correlation attack. First is about the column-wise correlation attack. In this attack, we assume the malicious service provider know the column-wise correlation, which is represented use a set J. Each element in a set is a joint distribution between 2 different attributes in the database. After receiving a fingerprinted database, the attacker can calculate an empirical column-wise correlation from the database, and he will launch the attack in a way such that he finds some entries in the fingerprinted database that are can potentially change or cause large discrepancy between the column-wise correlation in her prior knowledge and the column-wise correlation calculated from the data. And on the right, it is the pseudocode for the attack. So essentially, for each pair of the attribute and for all the possible values the attribute can take, the attacker calculated the differences between the joint distribution before and after fingerprint. As long as this is larger than a threshold, he will launch his attack on those selected entries. Similarly, in the row-wise correlation attack, we assume the attacker knows the row-wise correlation among individuals. So in this paper, we assume that only individuals in the same community are highly correlated. So the row-wise correlation information is denoted by the set S, and each element in the set S is the correlation between user I and between individual I and J in the same community, and their distance is defined as an exponential decay function. Similarly, when the database receiver obtains a fingerprinted database, he will first calculate an empirical row-wise correlation from the database, and then he launches the attack by flipping the least significant bits in each row that can lead to the large discrepancy between S and S prime. And this is a pseudocode for the row-wise attack. Essentially, he checks if these cumulative differences before and after fingerprint is higher than a predetermined value. He will launch attack on those rows that are satisfied in this condition. In the experiment, we show that the row-wise correlation attack actually preserve more database utility because it only changes a very few rows in the database. So now let me first show the vulnerability of an existing fingerprint scheme against the identified correlation attack. And we use 128-bit for the fingerprint string. In favor of the attacker, we assume that the attacker's priority on the column and the row-wise correlation are actually identical with the correlation from the correlation knowledge of the database owner. In other words, we let J equals to J prime and S equal to S prime. And we consider the census database as an example, which are all categorical attributes. And to insert fingerprint in this categorical database, we first need to encode the categorical values into integers. And we define two fingerprint robustness metric. The first is number of compromised fingerprint bits. It just counts the number of mismatches between the attacker's fingerprint bit and the fingerprint extracted from the liquid database. The next is accusable ranking. In particular, if a service provider is accusable ranking is R, it means it is the top R prime suspect among all the service providers who have received the database. And in the experiment, we consider that the database owner have shared her database for 1,000 times. So if an attacker ranks top 1 accusable, it means it is highly suspicious for the data leakage. If 50%, then he is just modest suspicious. If R equals 99%, it means that with very high probability, the database owner will accuse other innocent service providers for data leakage. This slide shows the attacking performance of the proposed correlation attack. So on the blue cell is the attacking result for the column-wise correlation attack. And we see that it is able to compromise or destroy 82 fingerprint bits among a total of 128. And at a cost of only less than 30% entries being changed in the fingerprint database. As a result, it makes the attacker only ranks about 90% accusable. So in other words, after launching the column-wise correlation attack with high probability, the database owner will accuse other innocent service providers for the data leakage. The blue cell is the attacking performance on the row-wise correlation attack. And we can see that it actually requires even less change in the fingerprint database to compromise a larger amount of fingerprint bit. And if on top of the row-wise correlation attack, we further launches a row-wise correlation attack. if on top of the row-wise correlation attack, we further launches a sequence of column-wise correlation attack, then at the end, 83 fingerprint bit is compromised at the cost of only 15% of the entries being changed. So to show the powerful attacking ability of the identified correlation attack, we compare with the random bit flipping attack, and we let the attacker only flipping this much percentage of the entries in the database, and these values are identical with that obtained from the column-wise correlation attack. And we see that if the attacker randomly changes 27% of the entries, then it is only able to compromise 4 fingerprint bit and will make this malicious user being uniquely accusable for the data leakage. We would like to highlight that the vulnerabilities are actually widespread in existing fingerprint schemes. Now with that, I'm going to talk about the corresponding mitigation techniques. I would like to first highlight the proposed mitigation technique can be served as a post-processing steps for any of the vanilla fingerprinting scheme. In other words, we can make any fingerprinting scheme robust against the identified correlation attack. The design goal of the mitigation is to let the database owner uses her prior knowledge on the column-wise and row-wise correlation to change only a few entries in a vanilla fingerprinting scheme database. And we want to make sure after the mitigation, the new database has column-wise correlation close to the prior knowledge of the column-wise correlation. But the new result will also have row-wise correlations that are far from her prior knowledge. Let me first talk about the column-wise mitigation technique. And we develop such mitigation based on the idea of optimal transportation, which is a tool to move the mass of the probability distribution function to make it looks like another PDF. So in our study scenario, the PDF being changed is the marginal distribution of a vanilla fingerprinting database. And we want to change their marginal distributions such that after change, the distribution will look similar to the ones in the prior knowledge, because you can obtain the ground truth marginal distribution by marginalizing the joint distributions. And the optimal transportation plan is used to change the entries in the attribute in each attribute of the database. So let me explain the idea using a toy example. In this table, on the first row is the marginal distribution of some attribute after fingerprint, and the second row is the ground truth marginal distribution. So we want to manipulate or change the first PDF to look like the second one. This is done by solving this object optimization problem. So essentially, the decision parameter is a mass transportation plan. So we want to obtain a mass transportation plan such that the cost of the mass transportation is minimized. And we have a tuning parameter for it. We can see for a higher tuning parameter, the transportation tends to only move the mass of one particular probability to its adjacent entries, but with smaller lambda, it means that this plan will tend to move the mass of a specific probability to over all the possible places. For example, when lambda p equals to 50, then the probability mass of the attribute taken value 0 is divided into multiple chunks and then moved to many other instances. So a smaller lambda means that the database owner will need to make more change in the fingerprinting database. And in the experiment, we need to strike a balance between the database utility and the mitigation performance. In the row-wise mitigation, we need to make sure that after the mitigation, the statistical relationship of the new database are far away from the prior knowledge. And we want to make it far away from the prior knowledge is because we want to avoid the large utility degradation. Because if we want to make the statistical information that is close to her prior knowledge, then it will lead to a significant amount of change in the mitigation. And in the experiment, we show that by doing this, it is already enough to mislead the malicious service provider to owning attack on those non-fingerprinted entries. The row-wise mitigation technique is essentially formulated by this optimization problem. So we let QC be the set in a community that has not been fingerprinted. So to conduct the row-wise mitigation, we essentially first choose a subset in the community that has not been fingerprinted yet. And then for those rows in the selected set, we change their value such that after change, the pairwise distance is not updated as SIJ double tilde. And after updating, we want to make sure that this new distance can maximize this total distance, which essentially means after the mitigation, the differences between cumulative pairwise distance is maximized so as to mislead the malicious service provider to only attack on the non-fingerprinted entries. Now let me talk about the mitigation performance. I have discussed the robust metric in the previous slides. And in the paper, we also consider different utility metrics. They are the accuracy of the database and the preservation of column-wise, row-wise, and the conventional metrics of the database. For all these four metrics, the higher the value, the better the utility. And just to recall that we need to solve this optimization problem to strike a balance between the mitigation performance and the utility. And we say that when lambda equals to 500, we get a decent value of database utility. So in the following slides, we set lambda equal to 500. And recall the first table is the correlation attack. And for example, in the last cell, highlighted in red, this is the attacking performance of the integration of row-wise and column-wise correlation attack. So we know by launching the integrated correlation attack, the attacker can compromise a total of 83 fingerprint bits. But if he launches the same attack after the database owner have conducted the mitigation technique, then it is only able to compromise 4 fingerprint bits. So there is a significant reduce from 83 to 4. As a result, if he leaks the database, it will be uniquely accusable by the database owner. Now is a conclusion. So in this paper, we identify correlation attack, show the vulnerability of existing scheme against the attack, and also develop a robust fingerprinting for databases. In the future, we will consider the collusion attack between different malicious service provider with different set of prior knowledge. And we also want to develop a collusion resistant robust fingerprinting by integrating the BS code. Finally, our work is supported by National Library of Medicine and the National Institute of Health. and I can be reached through this email should you have any questions. Thank you.